What created the universe? That single question may be the oldest and most profound inquiry humanity has ever asked. Every civilization, every culture, and every generation of thinkers has stared into the night sky and wondered, how did all of this come to be? Where did the stars, the planets, the galaxies, space itself, and even time originate? Did the universe emerge from some divine intention? Was it birthed by an impersonal force of nature? Or did it simply come from nothing? Among the many competing theories that attempt to answer this mind-shattering question, the most widely accepted scientific explanation today is the Big Bang Theory. It doesn't just speculate how the universe began. It provides a model, a framework grounded in observations, physics, and cosmology. But the deeper we look into it, the stranger it becomes. The term Big Bang may conjure images of an explosion, as if the universe suddenly blew up like a bomb in space. But that's not quite right. The Big Bang wasn't an explosion in space. It was an expansion of space itself. To understand this, we have to set aside our everyday intuition, because the Big Bang Theory challenges nearly every basic assumption we make about existence. According to the Big Bang Theory, around 13.8 billion years ago, the entire universe, everything you can see, everything you can't see, even the very fabric of space and time, was compressed into a state of infinite density and temperature. This state is what scientists call a singularity. At this singularity, all the laws of physics, as we know them, break down. General relativity, quantum mechanics, none of them work in the same way under these extreme conditions. It wasn't just matter and energy that were tightly packed into this point. Space itself didn't exist yet. Time didn't exist yet. The singularity was a point of no dimensions, and yet it somehow contained the blueprint for the entire cosmos. Then something happened, something inexplicable, something without a clear cause, at least not one we currently understand. This singularity began to expand, not into space, but as space. Time began to tick forward. Space began to stretch. Matter and energy began to cool and form structures. In the tiniest fraction of a second, a timescale known as the Planck time, just seconds, the universe grew from a point smaller than an atom to something much, much larger. This initial phase of the universe's expansion was governed by unimaginable forces. Temperatures were so high that no particles could exist as stable matter. Instead, the universe was filled with a seething plasma of quarks, gluons, and leptons, elementary particles interacting with radiation in a chaotic dance. As the universe continued to expand, it began to cool. This cooling allowed for new kinds of interactions to occur. Within seconds, particles began to form protons and neutrons. Within minutes, those particles formed the nuclei of light elements like hydrogen and helium. This process, known as Big Bang nucleosynthesis, created the first atoms that would eventually seed all the stars and galaxies. Fast forward a few 100,000 years. The universe was still glowing with intense radiation, but it was finally cool enough for electrons to combine with protons and form neutral hydrogen atoms. This process, known as recombination, allowed light to travel freely through space for the first time. That light is still with us today. It's called the cosmic microwave background radiation, or CMB, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. The CMB is a faint glow of microwave radiation that permeates the entire sky. It's the oldest light we can observe, and it's a fossil of the early universe. Its uniformity and subtle fluctuations provide a snapshot of the universe, as it was just 380,000 years after the Big Bang. When scientists look at the CMB, they are literally looking back in time, almost all the way to the birth of the cosmos itself. But the Big Bang Theory is not based on CMB alone. Several lines of evidence support it. First, there's the redshift of galaxies, a phenomenon discovered by Edwin Hubble in the 1920s. Hubble observed that galaxies were moving away from us, and the farther away they were, the faster they appeared to recede. This observation meant the universe was expanding. Not only was it expanding, it had been smaller in the past. Trace that expansion back far enough, and you reach a point of origin, the Big Bang. Second, there's the abundance of light elements in the universe. Hydrogen and helium make up about 98% of all ordinary matter. The Big Bang theory precisely predicts this ratio based on the processes that occurred in the first few minutes of cosmic history. No other theory has been able to match this prediction so accurately. Third, there's large-scale structure formation. Galaxies, clusters of galaxies, and vast cosmic filaments all form from the initial fluctuations seen in the CMB. The distribution of matter across the universe today, what we see in large sky surveys and simulations, matches what the Big Bang predicts, especially when combined with models of dark matter and dark energy. But even with all this evidence, the Big Bang theory isn't a complete answer to the question of what created the universe. It tells us how the universe evolved from an early hot and dense state, but it doesn't explain what caused that state to exist in the first place. It doesn't tell us what came before the Big Bang, or whether that question even makes sense, since time itself may have begun at that moment. There are other mysteries as well. For instance, why is the universe so flat? In geometry, a flat universe means one that isn't curved inward or outward on large scales. The Big Bang theory predicts some curvature unless the early universe had precisely the right conditions, a situation that seems almost too perfect. This is called the flatness problem. There's also the horizon problem. Opposite sides of the observable universe look nearly identical in temperature, even though, according to the speed of light, they should never have been in contact. How did they become so similar without ever interacting? To resolve these problems, scientists introduced the idea of cosmic inflation, an ultra-fast exponential expansion that occurred in the first fraction of a second after the Big Bang. Inflation could stretch out any initial curvature, making the universe appear flat. It could also allow distant regions to once have been close enough to interact, explaining the uniformity of the CMB. But inflation itself isn't fully understood. It requires a field, a kind of energy known as the inflaton field, and we still don't know what that is. Moreover, some models of inflation lead to even stranger possibilities, like the creation of multiple universes or pocket universes, each with its own physical laws. So, while the Big Bang theory is the dominant cosmological model, it leaves many questions unanswered. It describes what happened, but not necessarily why. It brings us tantalizingly close to the origin of everything, only to leave us standing at the edge of a mystery too vast to fully comprehend. And that's where the Big Bang ends and other theories begin. Some offer extensions to the Big Bang, while others challenge it entirely. They dive into the quantum world, question the nature of time, explore the idea of other universes, and even suggest that reality might not be what it seems at all. But to truly explore what might have created the universe, we need to look beyond the Big Bang. As the universe expands before our intellectual gaze, we step away from the grandeur of the Big Bang theory and dive into the realm of the microscopic, the subatomic, the quantum. While the Big Bang tells us how the universe evolved from a hot, dense beginning, it doesn't quite tell us why it began. So, what if the answer doesn't lie in stars or galaxies or cosmic radiation, but in the tiniest fluctuations of nothingness? This brings us to the quantum fluctuation theory, a radically different and deeply fascinating idea. It suggests that our universe may have emerged from what we would typically call nothing, but in quantum mechanics, nothing isn't truly empty. It's alive with possibility. It's a storm of spontaneous, fleeting events called quantum fluctuations. This is not speculation. It's rooted in the most tested theory in all of physics, quantum field theory. So what exactly is a quantum fluctuation? In the quantum realm, even the vacuum, the emptiest possible state, boils with energy. Quantum fields, which permeate all of space, are never perfectly still. Instead, they experience temporary, spontaneous changes in energy levels. These fluctuations produce pairs of particles and antiparticles that pop into existence and then annihilate each other in the blink of an eye. This happens all the time in what we call the vacuum of space. What looks like nothing is actually a roiling sea of activity. Now imagine a fluctuation so powerful, so improbable yet statistically permitted, that it doesn't collapse back into nothingness. Instead, it inflates rapidly, exponentially, chaotically. It expands and becomes something more. According to quantum fluctuation theory, this is how our universe may have been born, as a random fluctuation in a quantum vacuum. In this view, there was no cause in the traditional sense, no divine trigger, no grand mechanism, just the laws of quantum mechanics operating on the vacuum. One fluctuation among countless others gave rise to a bubble of spacetime. That bubble expanded, cooled, evolved, and eventually became everything we now see. Galaxies, stars, planets, life, thought. But to fully appreciate this theory, we must first understand the nature of the quantum vacuum. Unlike classical vacuums, which are truly empty, a quantum vacuum is the lowest energy state of a field. It's not nothing in the traditional sense. It's more like a container filled with potential. Even in its lowest energy state, it's subject to uncertainty due to Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like energy and time, cannot both be precisely known. This principle allows for temporary violations of energy conservation, as long as they happen quickly enough. And that's the loophole quantum fluctuations exploit. For infinitesimally short periods, the vacuum can violate the conservation of energy, creating particles out of nothing. Normally, these particles vanish just as quickly as they appear. But if a fluctuation lasts long enough and is governed by the right physics, say, the presence of a scalar field that can drive inflation, it could spawn a universe. Stephen Hawking and others have explored this idea deeply, particularly in the context of quantum cosmology. Hawking, in collaboration with James Hartle, proposed that the universe could have spontaneously emerged from a quantum vacuum without a boundary or a cause, using a path integral approach from quantum mechanics. More on that in the no-boundary proposal section later. But the underlying quantum fluctuation idea remains essential. Here's what makes this theory even more astonishing. It doesn't violate any known laws of physics. In fact, it might be the most natural consequence of combining quantum mechanics and general relativity, the two great pillars of modern physics. It aligns with what we see in the laboratory. Particle accelerators like the Large Hadron Collider have confirmed that the vacuum isn't empty. Virtual particles affect the outcomes of experiments. The Casimir effect, for example, demonstrates that even in a perfect vacuum, measurable forces arise due to quantum fluctuations. But how can such a minuscule, chaotic event lead to an entire universe? The key is inflation, a brief but exponential expansion of space that could stretch a tiny quantum fluctuation into something vast. According to inflationary models, a scalar field called the inflaton field could have powered this expansion. Once triggered, it would cause a microscopic patch of vacuum to expand faster than the speed of light, which doesn't violate relativity since space itself, not objects within space, is expanding. This process would magnify tiny quantum disturbances into large-scale cosmic structures. Those tiny initial fluctuations, inflated across the fabric of space, became the seeds for galaxies and clusters. In other words, the very structures of the cosmos, the great filaments of matter and voids between them, are direct imprints of quantum jitters in the earliest moments of time. That's not poetry, it's what the data suggests. The cosmic microwave background radiation contains the fingerprints of these fluctuations. The anisotropies, the small variations in temperature, are interpreted as relics of quantum perturbations from the inflationary era. The quantum fluctuation theory, then, is not just a wild idea. It is embedded in mathematics, supported by observation, and extrapolated logically from our best understanding of nature. Still, critics raise valid questions. If the universe emerged from a quantum fluctuation, what determined the laws of physics within it? Why does our universe appear to be fine-tuned for life? Could there be countless other fluctuations giving rise to other universes with different constants? If so, we are entering the territory of the multiverse, a topic we will explore soon. But perhaps the biggest philosophical consequence is this. The quantum fluctuation theory removes the need for a prior cause. It challenges our classical intuition that something must come from something. In the quantum world, that rule may simply not apply. The universe may not require a creator, a spark, or even a plan. It may have happened because, according to the laws of quantum mechanics, it could. This leads us to a hauntingly simple conclusion. If nothingness is unstable, and quantum mechanics governs all of reality, then the creation of a universe like ours may not just be possible. It may be inevitable. As we move forward from the quantum vacuum and its rippling fluctuations, we are naturally led into the grander idea of the multiverse. What if the universe we observe, its galaxies, stars, and even the laws of physics themselves, are not unique? What if they are but one pocket of a much larger and more diverse cosmic structure, teeming with other universes, each with their own rules, dimensions, and realities? The multiverse theory is not a single unified idea, but rather a collection of overlapping and interrelated concepts, each suggesting that our cosmos may be just one of many. These universes, together forming the multiverse, may exist simultaneously, causally separated from one another and governed by different physical constants. To begin understanding this theory, it's useful to explore its multiple levels as proposed by physicist Max Tegmark, who categorized multiverse hypotheses into 4 hierarchical types: Level 1, Level 2, Level 3, and Level 4. Let's start with Level 1, the infinite universe. According to Level 1, if space is infinite and the distribution of matter is uniform on large scales, as observations suggest, then it must contain infinite variations of matter configurations. In such an infinite cosmos, there are infinite Hubble volumes like ours. Eventually, due to the limits of probability, those configurations must begin to repeat. There would be another Earth somewhere with people identical to us having this same conversation. It's a chilling idea, grounded in nothing but the raw implications of an infinite volume and statistical certainty. Then there is Level 2, bubble universes, which arises naturally from eternal inflation, a model that we will explore in detail later. According to this idea, inflation doesn't happen just once. Instead, it continues eternally in some regions of space, creating isolated bubbles where inflation stops and a local universe like ours is born. Each bubble can have its own laws of physics, its own constants, its own dimensionality. Some may contain galaxies and life. Others may collapse or expand too quickly to allow complexity. In this multiverse, the constants of nature are like rolling the cosmic dice. We live in a bubble where the dice rolled favorably for life, but that's just one of countless bubbles. Level 3 takes us into quantum territory through the lens of the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event with multiple possible outcomes actually causes the universe to split, creating parallel realities for each outcome. Each time an atom decays, a coin flips, or a choice is made, the universe branches and each possibility becomes real in a different universe. This branching doesn't require new spatial regions. It happens in the same space, just in orthogonal quantum branches. You chose tea in one universe, coffee in another. You lived in one, died in another. This version of the multiverse challenges our notions of identity, consequence, and determinism. Finally, there is Level 4, the ultimate ensemble. Here, we return to Tegmark's boldest claim, that all mathematically possible structures exist. Any reality that can be described by mathematics exists somewhere in the multiverse. This is not merely science fiction. It's a philosophical assertion rooted in the assumption that mathematics is not just a tool we use to describe reality, but the very fabric of reality. We will delve more deeply into Tegmark's mathematical universe hypothesis later. But for now, understand that Level 4 implies the widest possible multiverse, one where not just physical constants vary, but the very logic and structure of existence itself. Returning to the broader view, the multiverse theory serves as a natural extension of other theories rather than standing entirely alone. It emerges from inflationary cosmology, quantum mechanics, and string theory. It is less an invented idea than an implication, a consequence of the mathematics if we take our current theories seriously and follow them to their logical conclusions. One of the most compelling motivations for the multiverse is the fine-tuning problem. The laws of physics appear exquisitely tuned to allow the existence of life. If the gravitational constant were slightly weaker or stronger, stars wouldn't form. If the strong nuclear force were just a bit off, atoms wouldn't hold together. The same goes for the charge of the electron, the cosmological constant, and dozens of other values. This improbability cries out for explanation. In a single universe model, we might resort to the Anthropic principle, which says that we observe a universe compatible with life because otherwise we wouldn't be here to observe it. But in a multiverse, the Anthropic principle gains more power. There are countless universes with different constants, most of them sterile and lifeless. We find ourselves in a life-permitting one not because it's special, but because it had to happen somewhere, and we can only exist in such a place. This idea transforms cosmic fine-tuning from an impossible coincidence into a statistical certainty across a vast ensemble. There is also indirect support for the multiverse from string theory, which posits a vast landscape of possible vacuum states, on the order of 10 to the power of 500 or more, each corresponding to a universe with its own set of physical laws. This string landscape fits naturally into the Level 2 multiverse, where each bubble universe settles into a different valley of this vast landscape. Still, skeptics raise serious concerns. Chief among them is falsifiability. How do we test the multiverse if other universes are causally disconnected from ours? If no experiment can confirm or deny their existence, is the multiverse even science? These are legitimate philosophical questions, but defenders argue that if our best theories predict a multiverse, and those theories are supported by observation in other ways, then the multiverse should be taken seriously, just as we accept black holes or quarks long before directly observing them. Occasionally, some models predict potential signatures of other universes in the cosmic microwave background, such as unusual cold spots or circular patterns resulting from collisions with neighboring universes. While tantalizing, such evidence remains tentative and controversial. Even without direct proof, the multiverse offers explanatory power. It makes sense of a universe's properties, it aligns with known physics, and it suggests that reality is far more vast and varied than we ever imagined. But the implications are profound. If the multiverse is real, then everything that can happen does happen. Somewhere. There are universes where you made different choices, where Earth never formed, where stars never ignited, where civilizations evolved in unimaginable ways. It forces us to rethink identity, morality, meaning. Are we just one flickering candle among infinite flames? And yet, far from making life meaningless, the multiverse can make it more precious. The very rarity of our configuration, the delicate balance of our universe, gives it weight. We are not just possible. We are improbable, and therefore wondrous. As we look into the sky, we no longer see the whole cosmos. We see merely one room in an endless mansion, one note in a symphony that spans infinite octaves. The eternal inflation theory emerged as a natural evolution of the inflationary model, which was first proposed in the early 1980s by physicist Alan Guth. The original idea was affixed to a set of problems in the classical Big Bang model, such as the horizon problem, the flatness problem, and the monopole problem. Inflation proposed that, in the earliest moments after the universe began, it underwent a period of exponential expansion, growing faster than the speed of light for a tiny fraction of a second. This rapid inflation smoothed out the wrinkles in the early universe and created the conditions that we now observe. Large-scale uniformity, temperature balance across vast regions of space, and the absence of relics like magnetic monopoles. But soon after the inflationary theory was proposed, physicists realized that inflation might not be a one-time event. In fact, it might be an eternal process. This is the core of eternal inflation, a concept that fundamentally transforms our picture of the cosmos. The key insight is that inflation is driven by a hypothetical field called the inflating field. This field is thought to possess a certain amount of energy, and as long as it remains in a high-energy state, space will continue to expand at an exponential rate. However, in small localized regions, quantum fluctuations can cause this field to decay into a lower energy state, releasing energy in the form of particles and radiation, the stuff of stars, galaxies, and life. This localized decay is what we call the birth of a universe, or more accurately, a pocket universe. The critical realization is this: while some regions of space decay and stop inflating, other regions continue to inflate. Due to the nature of the quantum fluctuations in the inflating field, there will always be regions where inflation continues forever. These ongoing inflating regions constantly spawn new pocket universes, each causally disconnected from the others, and each potentially with its own laws of physics, particle configurations, and cosmic histories. This is why we call it eternal inflation. Once it starts, it never completely stops. It's like a firework that continually explodes, and from each explosion comes more fireworks, each forming its own unique burst of light and color. The inflating space expands so fast that even as some areas stop and form pocket universes, the volume of space still inflating keeps growing. There's always more, always expansion, always the potential for new universes. These pocket universes are what we perceive as the multiverse in the level 2 category discussed earlier. But eternal inflation provides a mechanism for how these universes are created, not just the possibility. And it does so using physics that arises naturally from quantum field theory and general relativity. This idea has profound implications. It suggests that our universe is just one bubble in a cosmic foam, perhaps infinite in extent, with an ever-growing sea of new universes blossoming into existence every moment. Each bubble might have a different value of the fundamental constants, different laws of physics, or even different numbers of spatial or temporal dimensions. One of the most compelling aspects of eternal inflation is its ability to make the universe self-replicating. It is a cosmological fractal, a never-ending, self-similar structure in which each part is a small reflection of a larger whole. Some cosmologists even liken it to a kind of biological process, where the cosmos undergoes reproduction on a cosmic scale. There is also a deeply philosophical consequence of eternal inflation, the idea of cosmic inevitability. If inflation goes on forever and creates infinite universes, then anything that can happen will happen infinitely many times. This includes universes like ours, with life, Earth, and everything you know. It also includes bizarre universes where the laws of physics take entirely different forms. The universe becomes a vast, probabilistic ocean, and we are simply one wave upon it. This leads to the measure problem in cosmology. If there are infinite universes, how do you assign probabilities to events? If every event happens infinitely often, how can you say what's likely or unlikely? This is still an unresolved issue in theoretical physics, and different physicists propose different ways of cutting off the infinities to extract meaningful predictions. In terms of observation, eternal inflation, like the multiverse, is challenging to test directly. Our pocket universe is causally disconnected from others, and inflation wipes out any traces of what came before it. However, some speculative ideas suggest that if two bubble universes collide, they might leave a scar in the cosmic microwave background, a circular pattern or cold spot. There have been searches for such patterns, and while some anomalies exist, no definitive evidence has emerged yet. Nonetheless, the theory remains appealing because of its natural emergence from established physics. We don't need to invent new frameworks or particles out of nowhere. Eternal inflation arises when we take quantum fields seriously in a rapidly expanding spacetime, and when we allow for randomness and decay. It is not a fantasy bolted onto cosmology. It is an extrapolation of the very tools we already use. Another consequence of eternal inflation is the concept of a beginningless universe. In many models of eternal inflation, there is no single moment of creation, no first universe. Inflation has always been happening, eternally into the past and future. Other models suggest that while inflation is eternal into the future, it may still have had a beginning in the past, perhaps linked to the Big Bang or some other quantum gravitational event. This question, whether eternal inflation is truly eternal in both directions, remains a hotly debated topic in cosmology. Then there's the cosmic multiverse landscape as predicted by string theory, which dovetails elegantly with eternal inflation. String theory allows for a vast number of possible vacuum states, on the order of 10 to the power of 500 or more, and eternal inflation provides a natural way for the cosmos to explore this landscape. Each new pocket universe may land in a different valley of this potential energy terrain, resulting in different physics. This creates a cosmic Darwinism, where the Anthropic principle plays a role in determining why we find ourselves in a universe like ours. Eternal inflation doesn't just predict multiple universes. It predicts an endless unfolding of possibility, a cosmic engine that continuously births complexity, diversity, and structure across infinite scales. And yet, eternal inflation raises as many questions as it answers. Is there a way to test it? Can we ever observe another bubble? Will we ever understand the full structure of the inflating field? Could our universe be just a simulation of a bubble inside another universe? The implications are staggering, and the answers may lie forever beyond our reach, or they may be discovered by the next generation of physicists and astronomers. For now, eternal inflation stands as one of the most powerful and comprehensive explanations for why our universe exists, why it looks the way it does, and why we find ourselves here asking these questions. It unifies the physics of the very small with the structure of the very large. It opens the door to infinity, and it whispers that we are not alone, not just in terms of life, but in terms of realities. Now we move into the fascinating realm of the cyclic universe theory, a model that challenges the conventional idea of a single beginning and end to the universe. Unlike the Big Bang model, which implies that time and space originated from a singular explosive event, the cyclic universe offers an eternal rhythm of birth, death, and rebirth. It's a theory that echoes ancient philosophical and mythological ideas of universes emerging and dissolving like the breath of a cosmic being, but it's rooted in modern physics and mathematics. The core premise of the cyclic universe is that the universe undergoes endless cycles of expansion and contraction. In each cycle, the universe is born, evolves, expands, slows down, and then contracts back into a hot, dense state, only to bounce back again into a new expanding phase. This process could continue infinitely into the past and future, suggesting that our current universe is merely one in a potentially unending chain. There are different versions of the cyclic model, each with unique physical mechanisms to explain the bounce, the transition from contraction to expansion, but all share the central idea that the universe has no true beginning or end. Instead of a singular creation event like the Big Bang, we have a cosmic heartbeat, eternally pulsing. One of the most notable versions of the cyclic model was developed by physicists Paul Steinhardt and Neil Turok, who drew from string theory and brain cosmology to build a model often referred to as the Ekpyrotic universe, which we'll explore in more detail in the next section. But even independent of string theory, the cyclic universe has roots that go back to some of the earliest models in general relativity. In traditional general relativity, it is theoretically possible for a closed universe, a universe with positive spatial curvature, to undergo a cycle of expansion and collapse. In this picture, gravity eventually halts the expansion and reverses it, pulling all matter back together into a big crunch, followed by a potential Big Bang or rebound. The problem, historically, was that entropy, the disorder in the universe, would increase with every cycle. Eventually, the universe would be dominated by disorder, heat death, and unusable energy. This was a major obstacle to any serious consideration of cyclic models. But recent ideas challenge this view. Modern cyclic universe theories aim to reset the entropy clock at the end of each cycle. They incorporate mechanisms to dilute or remove entropy before the bounce, allowing each new cycle to begin fresh, or at least with low enough entropy for structure, stars, and galaxies to reform. These mechanisms often rely on modifications to general relativity or extensions into quantum gravity or string theory. In the Steinhardt-Turok model, for instance, the universe is described not as a single three-dimensional bubble, but as a three-dimensional brane, short for membrane, embedded in a higher dimensional space called the bulk. Our universe is one such brane, and there may be another parallel brane close by, separated in the bulk by an infinitesimal distance. According to this theory, the Big Bang wasn't the beginning of everything. It was the result of a collision between these two branes. The energy released by the collision heated the universe and filled it with matter and radiation, initiating a cycle of expansion. Over billions of years, the branes move apart again, the universe expands and cools, and then the branes are drawn back together due to the force of a scalar field in the bulk. When they collide again, another Big Bang happens, and the cycle begins anew. What makes this cyclic model particularly intriguing is that it explains many of the same features of the universe that inflationary theory does, such as the homogeneity and isotropy of the cosmic microwave background, but without needing a rapid inflationary phase. Instead, the uniformity comes from the stretching of the brane over long time scales in each cycle, which smooths out any irregularities. Another major advantage of the cyclic universe is that it resolves the initial singularity problem. In the Big Bang model, the universe originates from a point of infinite density and temperature, a singularity where the laws of physics break down. In the cyclic model, there is no singularity. The bounce replaces the singularity with a well-defined transition, a handoff from contraction to expansion governed by known, or yet to be fully understood, physics. This has deep implications. If the cyclic universe is correct, then our universe never began and it will never end. The arrow of time, which we usually associate with entropy and the forward flow of events, may reset or even reverse at the bounce. Some versions of the theory suggest that time itself may be an emergent property of the cycle, arising from deeper, timeless principles. Another fascinating implication is cosmic memory. If the universe has undergone countless cycles before, could anything survive from a previous cycle into the next? In most cyclic models, the answer is no. Each cycle wipes the slate clean. But some speculative ideas entertain the possibility of quantum relics, black hole information, or even subtle imprints in the cosmic microwave background that might carry echoes of a prior cosmos. These are highly speculative and remain purely hypothetical, but they add a poetic dimension to the theory. Critics of the cyclic model often point out that there is no direct observational evidence of prior cycles. The observable universe shows no clear signs of a previous contraction phase. Furthermore, the physics of the bounce is still not completely understood, especially within the framework of classical general relativity. Some models rely on hypothetical fields or particles that haven't been detected. Yet despite these challenges, the cyclic universe has persisted as one of the boldest and most beautiful ideas in cosmology. It offers an elegant alternative to the concept of a cosmic beginning, aligns with principles of symmetry and recurrence found throughout nature, and paints the universe not as a one-time event, but as an eternal, ever-unfolding story. The cyclic universe model also inspires philosophical reflections. In a cosmos with no beginning and no end, the question, what created the universe, becomes reframed. There may be no need for a cause or creator in the traditional sense, because the universe always was and always will be. Causality becomes a closed loop, and the divine spark, if one seeks it, may lie not in a first cause but in the eternal dance itself. As our understanding of physics deepens, particularly in the realms of quantum gravity, string theory, and higher dimensions. The cyclic universe continues to be a fertile ground for exploration. Whether it ultimately proves correct, it challenges us to think beyond beginnings and ends, to consider a cosmos that pulses forever, and to recognize that the mysteries of creation may lie not in a bang, but in a cycle. Now we dive directly into the Ekpyrotic theory, a profound and imaginative cosmological model that redefines how we might understand the origin of the universe. The word Ekpyrotic is derived from the ancient Greek term ekpyrosis, meaning conflagration or out of fire, originally used in Stoic philosophy to describe a cyclical destruction and rebirth of the cosmos through a cosmic fire. However, in modern physics, the Ekpyrotic theory represents a highly technical and structured attempt to explain the creation of our universe, not from a singularity, but from the collision of higher dimensional structures called branes. This theory was first introduced in the early 2000s by Paul Steinhardt, Neil Turok, and Justin Khoury, emerging out of developments in string theory and M theory, particularly concepts related to extra dimensions and the behavior of branes within higher dimensional space. At the heart of the Ekpyrotic model is the idea that our observable universe is a three-dimensional brane embedded in a higher dimensional bulk space. In this framework, the Big Bang was not the beginning of everything, but rather a dramatic event. Specifically, a collision between two parallel branes floating in a higher dimensional universe. One of these branes is thought to be our universe, and the other is a parallel universe that exists a tiny fraction of a millimeter away, but in a spatial dimension beyond our perceptual reach. The energy generated by the collision of these two branes caused the hot, dense state that we typically associate with the beginning of the universe, the aftermath of which was the rapid expansion and cooling that gave rise to all known matter and radiation. But this is not a singular event. In many versions of the Ekpyrotic model, this collision is part of a cycle, meaning it has happened before and will happen again, suggesting an eternal, self-renewing cosmos. The Ekpyrotic model was, in many ways, developed as a response to shortcomings in the inflationary Big Bang model. One of the central problems it seeks to resolve is the nature of the singularity, the point of infinite density and temperature where the laws of physics break down. Inflation theory avoids the singularity by proposing a brief period of exponential expansion, but it still requires the universe to emerge from a highly specific and finely tuned state. The Ekpyrotic model, in contrast, eliminates the singularity altogether by replacing it with a smooth transition caused by the brane collision. One of the most compelling strengths of the Ekpyrotic theory lies in its natural explanation for the large-scale uniformity and flatness of the universe. In the inflationary model, these properties are explained by a burst of rapid expansion that stretches out irregularities. In the Ekpyrotic model, the branes begin to slowly approach each other in a nearly parallel fashion over a long period, naturally smoothing out any inhomogeneities in the process. This slow contraction before the branes collide acts much like inflation in erasing any pre-existing wrinkles or fluctuations in spacetime. Additionally, the Ekpyrotic model generates cosmic perturbations, the tiny fluctuations in density that eventually led to the formation of galaxies and cosmic structure, without requiring quantum fluctuations during inflation. Instead, these perturbations arise from the slow and steady movement of the branes toward one another, and the way their separation influences scalar fields in the higher dimensional bulk. These scalar fields control the distance between branes and act as the driving force behind the cosmic evolution in this model. A fascinating and crucial component of the Ekpyrotic theory is the concept of the fifth dimension, often referred to as the bulk dimension in which the branes exist. In M theory, our familiar three spatial dimensions, along with time, are part of a larger framework involving up to 11 dimensions. The Ekpyrotic model leverages this idea by suggesting that the fifth dimension is where brane interactions occur, and it is this brane interaction that serves as the fundamental mechanism for cosmic creation. This higher dimensional view opens the door to incredible theoretical possibilities. For instance, the other brane, the one parallel to ours, could contain its own laws of physics, its own version of matter and energy, and potentially even its own intelligent life. Yet we are unaware of it because it exists in a spatial direction we cannot access or perceive. This gives the Ekpyrotic model a deep philosophical resonance, suggesting that our universe is not alone, but one of a pair, or even a multitude, within a grand multidimensional tapestry. However, as with all cosmological theories, the Ekpyrotic model faces significant challenges. One of the major obstacles is the bounce, the mechanism by which the collision of branes leads to an expanding universe without creating singularities or violating known laws of physics. In classical general relativity, such a bounce seems impossible due to the conditions imposed by energy and entropy. But modern versions of the theory incorporate modifications to gravity or quantum effects that could allow a bounce to occur smoothly. For example, recent developments in string theory-inspired Ekpyrotic models propose that the energy from the approaching branes gets converted into the matter and radiation of the new universe, much like inflation turns potential energy into thermal energy. Other versions incorporate ghost condensates or exotic scalar fields that violate standard energy conditions in a controlled way, enabling a non-singular transition. Another point of contention is the lack of direct observational evidence for branes, extra dimensions, or bulk scalar fields. These are predictions that lie far beyond current experimental capabilities, though some suggest that subtle imprints might eventually be found in the cosmic microwave background or gravitational wave data. For instance, a distinctive pattern of non-Gaussian perturbations in the early universe would lend support to the Ekpyrotic scenario over standard inflation. Despite these obstacles, the Ekpyrotic theory remains a rich and vibrant area of research, largely because it offers a viable and testable alternative to inflation and potentially solves many of the same cosmological puzzles without invoking an early phase of ultra-rapid expansion. It also provides a conceptual framework for incorporating string theory and higher dimensional physics into cosmology, giving theoretical physicists a platform to explore deep connections between particle physics, quantum gravity, and the origins of the cosmos. One of the philosophical implications of the Ekpyrotic model is that the universe is eternal and self-regenerating. There is no absolute beginning, no single act of creation, but rather an ongoing cycle of brane interactions that give birth to universes like ours. The question of what created the universe becomes, in this view, a question of what governs the dynamics of branes in higher dimensional space. It's not so much about the origin as it is about the mechanism, a subtle but profound shift in thinking. The cosmos may not need a creator or an initial cause in the traditional sense if the act of creation is woven into the fundamental behavior of the multiverse. In this light, the branes themselves are eternal entities, their motions dictated by fundamental laws that are still only partially understood and possibly unknowable from within the confines of a single universe. In conclusion, the Ekpyrotic theory represents one of the most ambitious and imaginative efforts to reframe our understanding of cosmological origins. It merges cutting-edge physics with ancient philosophical themes, challenges the prevailing paradigms of cosmology, and provides a tantalizing vision of a universe born not from nothing, but from the elegant choreography of higher-dimensional branes in an infinite cosmic ballet. Now we move into one of the most provocative and mind-bending ideas about the origin of the universe: the simulated universe hypothesis. This theory doesn't suggest the universe came from singularity, a brane collision, or quantum energy. Instead, it proposes that our entire reality, space, time, matter, and even consciousness, is part of an extremely advanced computer simulation created by a more intelligent civilization. The simulated universe hypothesis gained widespread recognition through the work of philosopher Nick Bostrom of Oxford University, who presented his influential paper in 2003 titled, "Are You Living in a Computer Simulation?" Bostrom laid out a trilemma, arguing that one of the following propositions must be true. 1. All civilizations at our current level of development go extinct before becoming technologically mature. 2. Technologically mature civilizations are not interested in running simulations of their ancestors. 3. We are almost certainly living in a computer simulation. This logic is based on a probabilistic argument. If we accept that it is possible for an advanced civilization to run many detailed simulations of their ancestors, and they choose to do so, then the number of simulated minds would vastly outnumber the number of real biological minds. Therefore, statistically, it is overwhelmingly more likely that we are one of the simulated minds than one of the original biological ones. So what does this mean in terms of the universe's creation? Under this hypothesis, the universe did not emerge naturally at all. It was intentionally created, but not by a divine being in the classical sense. Instead, it was programmed by a highly advanced intelligence, one capable of developing a hyperrealistic simulation indistinguishable from physical reality. This creator could be an alien civilization millions or billions of years more advanced than us, or even post-human descendants of our own species who developed such technology. The simulated universe would include not only planetary systems and galaxies, but also the laws of physics themselves. These laws would be rules coded into the simulation, governing how matter and energy behave. In this framework, constants like the speed of light, Planck's constant, or the fine structure constant are not eternal truths of nature, but parameters defined in code. This introduces a radical idea. Our reality is not objective, but virtual. The very atoms and particles we think of as fundamental could be data points, and what we experience as cause and effect could be programmed logic. Our perceptions, our thoughts, and even our sense of time could all be simulated phenomena managed by an underlying computational substrate. One of the philosophical advantages of the simulated universe hypothesis is that it provides a creator without invoking mysticism. The creator is not supernatural, but technological. And this creator did not make the universe for divine reasons, but possibly to run experiments, to simulate evolutionary pathways, to study consciousness, or even just for entertainment. Some scientists and thinkers have taken this hypothesis seriously and sought empirical ways to test it. For example, theoretical physicist Silas Bean and his colleagues proposed that a simulated universe might have built-in computational limitations, such as a maximum resolution or energy scale, akin to how pixels define the resolution of an image or how processing power limits what a video game can render. If such limitations exist in our universe, they might appear as anomalies in high-energy physics, such as constraints on cosmic ray behavior. Indeed, certain lattice-like artifacts could emerge in the universe's structure, betraying its artificiality. While these tests remain speculative and far from conclusive, the very attempt to falsify the simulation hypothesis reflects how seriously some regard it. There are also existential implications. If the universe is a simulation, it might be shut down at any moment. Perhaps the creators are observing us in real time, analyzing our behaviors, reactions, and societies. The apparent vastness of the universe might not be physically rendered until we look at it, echoing the quantum concept that observation affects reality. If this is true, we may not be observing the universe. The universe might be responding to our observation. Moreover, the hypothesis raises questions about free will. Are our thoughts and decisions programmed? Or is the simulation sophisticated enough to permit conscious experience and agency? If our brains are just nodes in a digital network, is consciousness a byproduct of computation, or is it something more? Interestingly, many ancient philosophical systems align loosely with this idea. Plato's allegory of the cave, for instance, depicted people experiencing only shadows of reality. These ancient ideas could be interpreted as early forms of the simulation hypothesis, suggesting humans have long intuited the unreality of their perceived world. Skeptics of the simulation theory argue that it suffers from unfalsifiability. If any evidence can be interpreted as part of the simulation's programming, and the simulation is constructed to appear fully natural, then how could we ever prove it? Furthermore, even if we are in a simulation, does it make any practical difference to how we live, make choices, or understand morality? Despite these critiques, the simulation theory continues to gain traction, especially with advancements in virtual reality, artificial intelligence, and quantum computing. As we ourselves move closer to the ability to create realistic simulations and artificial minds, the possibility that we are already in one becomes more plausible. Some physicists like James Gates have found strange patterns in the equations of supersymmetry that resemble error-correcting codes, the same kind used in modern computing. While this could be coincidental or a result of the mathematical structures we use, it adds fuel to the speculation that reality might be a construct rather than a continuum. The simulated universe hypothesis also opens the door to meta-universal thinking. If our universe is a simulation, is the one above it real? Or is that universe itself a simulation within a larger system? This leads to the idea of nested simulations, where simulations run other simulations, each level believing it is at the base of reality. This recursive view suggests that true reality may be fundamentally unknowable. Finally, the simulation theory addresses the question of what created the universe by implying it was designed not by divine intervention or natural forces, but by intelligent design through computation. It recasts the cosmos not as a physical entity, but as a virtual one, constructed to explore possibility space, consciousness, morality, or the fundamental nature of being. In a strange twist, if this theory is true, then everything we seek to understand, the stars, the laws of physics, even the idea of a beginning, are all part of a simulation running on an unknown machine by unknown creators. It is not just the origin of our universe that is mysterious. It is the origin of the simulation itself, a question that may be forever beyond our reach. Now we explore the steady-state theory, a once prominent cosmological model that offered a strikingly different explanation for the origin and structure of the universe, one that directly contradicted the Big Bang theory. Developed in the mid-20th century by Fred Hoyle, Thomas Gold, and Hermann Bondi, the steady-state theory argues that the universe has no beginning and no end. It is eternal, unchanging in its large-scale structure, and always looks roughly the same throughout time. At the heart of the steady-state theory is the perfect cosmological principle, which extends the traditional cosmological principle. While the standard cosmological principle states that the universe is homogeneous and isotropic in space, that is, it looks the same in every direction and at every location. The perfect version of this principle adds that the universe also appears the same at all points in time. It asserts that the large-scale properties of the universe do not change over time. This means, under steady-state logic, the universe was never created in the sense of a beginning. It has always existed and will always exist. There is no moment of creation, no singularity, no beginning of time, and no explosive origin event like the Big Bang. However, this creates an obvious problem. If the universe is expanding, as Edwin Hubble had observed, then it should be getting less dense over time. If galaxies are moving apart, the matter in the universe should become more spread out and diluted. But the steady-state model proposed a controversial solution: continuous creation of matter. According to the theory, new matter is constantly being created out of nothing to fill the gaps left by the expanding universe. As galaxies drift apart, new hydrogen atoms spontaneously appear in the void, eventually condensing to form new stars and galaxies. This ongoing process ensures that the density of matter in the universe remains constant, even as the universe expands. This idea may sound far-fetched, but mathematically, the amount of matter that would need to be created is surprisingly small, on the order of 1 hydrogen atom per cubic meter every billion years. The creators of the theory argued that such a minuscule rate would be impossible to detect, but it would be enough to maintain the steady-state conditions. One of the most significant strengths of the steady-state theory is its philosophical appeal. It avoids the uncomfortable idea of a beginning or creation event. The theory does not need a cosmic origin story, divine intervention, or a special moment of creation. It posits an eternal, self-sustaining universe, consistent with the laws of physics as they were understood at the time. Fred Hoyle famously criticized the Big Bang theory for its theological implications, even coining the term Big Bang sarcastically during a BBC radio broadcast. He found it distasteful that the Big Bang implied a creation moment that could be interpreted as aligning with religious creation myths. Hoyle and his colleagues saw the steady-state theory as a more scientifically grounded alternative, one that eliminated the need for a beginning. During the 1940s and 1950s, the steady-state theory had a strong following and was taken seriously by many cosmologists. It offered elegant explanations for the universe's apparent isotropy and expansion, and it presented a universe without paradoxes of origin or end. For a time, it was one of the leading cosmological models, standing shoulder to shoulder with the Big Bang. However, the steady-state theory began to face serious challenges with the advancement of observational cosmology, particularly in the 1960s. The most devastating blow came with the discovery of the cosmic microwave background radiation, CMB, in 1965 by Arno Penzias and Robert Wilson. The CMB is a faint glow of residual heat from the early universe, interpreted as the afterglow of the Big Bang. According to Big Bang cosmology, this radiation was emitted about 380,000 years after the universe's explosive origin, when atoms first formed and the universe became transparent to light. The steady-state theory could not account for the existence of this uniform background radiation. There was no event in steady-state cosmology that could produce such a background glow. The discovery of the CMB was considered one of the most direct pieces of evidence supporting the Big Bang and was a critical factor in the decline of the steady-state model. Further evidence against the steady-state theory came from observations of galactic evolution. In the steady-state model, the universe should always look the same at all times. Therefore, distant galaxies, which we see as they were billions of years ago, should look similar to nearby galaxies. However, astronomers observed that distant galaxies appeared younger, more irregular, and more active than closer ones. This suggested a changing universe, which directly contradicted the steady-state claim of timeless uniformity. Additionally, quasars, extremely luminous and energetic galactic cores, were found to be more common in the distant universe, implying they were more frequent in the early universe. This again conflicted with the idea that the universe looks the same at all times. These and other observations led to the steady-state theory falling out of favor in the scientific community. By the 1970s, it was largely abandoned by cosmologists, and the Big Bang theory became the dominant model of cosmic origin. Still, the steady-state theory is important in the history of cosmology for several reasons. First, it challenged scientists to test their assumptions, prompting deeper investigations into the structure and history of the universe. Second, it demonstrated the power of philosophical principles, like the perfect cosmological principle, in shaping scientific theories. Some modern variations of steady-state ideas continue to exist in the form of quasi-steady-state models or eternal universe proposals, but these are usually folded into more complex and modern theories, often borrowing concepts from quantum cosmology or string theory. Despite being largely discredited, the steady-state theory remains a bold and fascinating attempt to answer the question, what created the universe? Its answer was unique. Nothing created the universe because it was never created. It always was and always will be. The universe is eternal and self-sustaining, with new matter perpetually arising to maintain balance. In this view, creation is not an event but a process, a continuous, eternal unfolding of matter into form. It's a perspective that still resonates with some who seek a cosmos free from beginnings or ends. Now we venture into one of the most conceptually mind-bending and revolutionary ideas in modern theoretical physics, the holographic principle. This theory is not only a response to questions about the universe's origin, but also a profound rethinking of what space, time, and reality actually are. At its core, the holographic principle proposes that everything we perceive as three-dimensional, including space, matter, energy, and even time itself, might actually be a projection of information encoded on a distant, lower-dimensional boundary. Just as a hologram stores a 3D image in a 2D surface, This theory suggests our universe is a kind of cosmic hologram, and all the phenomena we experience within it are manifestations of that encoded data. This idea stems from attempts to resolve a profound paradox in physics, the black hole information paradox. In the 1970s, Stephen Hawking showed that black holes emit radiation, now called Hawking radiation, and can eventually evaporate completely. But this posed a dilemma. If a black hole disappears, where does all the information about the matter that fell into it go? According to the laws of quantum mechanics, information cannot be destroyed, but Hawking's results implied it might be. Physicists like Gerard T. Hooft and Leonard Susskind took on the challenge. They theorized that perhaps all the information about the particles that fall into a black hole is not lost, but instead is encoded on the black hole's event horizon, its two-dimensional surface. They argued that the surface area of a black hole, not its volume, determines how much information it can store. This was a radical departure from classical thinking, which would expect that information scales with volume, not surface. This led to a more general idea. If the information content of a black hole can be fully described by data on its boundary, maybe the same applies to the entire universe. In 1997, theoretical physicist Juan Meldacena provided a major breakthrough by proposing a concrete model known as the ADS/CFT correspondence. In this model, a theory of gravity in a five-dimensional space, anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity in four dimensions on the boundary of that space. In other words, gravity in the bulk could be completely described by quantum physics on the surface. This was the first solid evidence that a holographic duality could be more than just metaphorical. It could be a literal mathematical framework. Though our actual universe is not an anti-de Sitter space, this correspondence gave physicists a powerful new tool to explore the quantum structure of spacetime. The implications of the holographic principle are astonishing. It suggests that space is not fundamental. Instead, space, and perhaps even time, are emergent phenomena, arising from more basic informational structures. What we perceive as a continuous, flowing, 3D world may in fact be an illusion, a projection from a deeper, flatter layer of reality. This is analogous to how a computer screen displays a virtual world in a video game. The characters, objects, and landscapes appear to exist in a three-dimensional environment, but all of it is ultimately composed of binary data stored on a hard drive. Similarly, the atoms, stars, galaxies, and people in our universe may be akin to pixels generated from underlying quantum data on a cosmic boundary. One of the most profound consequences of this view is that the fundamental bits of reality are not located in space. They create space. Information is not stored in a specific region of space. Rather, space itself is the result of the entanglement of this information. This concept dovetails with research in quantum gravity, especially efforts to unify general relativity and quantum mechanics. In fact, some physicists believe that entanglement is the glue of spacetime. According to this view, the geometry of space and the force of gravity itself may arise from the intricate web of quantum entanglement among fundamental information bits. This is a central tenet of the broader research area called emergent gravity, which we will explore in more depth later. In practice, the holographic principle has provided new ways to tackle problems in black hole physics, thermodynamics, quantum information theory, and even high-energy particle physics. For instance, researchers use holographic dualities to study strongly interacting quantum systems that would be otherwise impossible to analyze with conventional methods. Moreover, this principle redefines the way we think about the origin of the universe. If space and time are emergent, then the universe did not necessarily begin as a point in space-time. It may have begun as a quantum information structure whose entanglement patterns generated the illusion of a Big Bang. In this scenario, the beginning wasn't an explosion in space, but a transition in the geometry of information itself. Some cosmologists propose that the universe we live in, what we think of as our 3D cosmic bubble, could be a projection from a 2D cosmological horizon. Others suggest that the universe is encoded on the surface of a much higher dimensional space. In either case, our universe becomes a kind of shadow, and reality exists not within the shadow, but on the screen from which it is cast. The holographic principle also changes how we might think about causality and time. In traditional physics, cause precedes effect within spacetime. But if spacetime is emergent, then cause and effect may arise from deeper relationships in the underlying information. What we perceive as the forward arrow of time could be the result of increasing entanglement or changing informational states. Furthermore, the principle might even help explain the mystery of dark energy. Some physicists speculate that dark energy, responsible for the universe's accelerating expansion, might be a byproduct of how information is distributed across the cosmological horizon. Others see connections between holography and entropy, suggesting that the expansion of the universe is related to the increase of entropy on a holographic screen. Despite its elegance, the holographic principle remains untested in a direct, observable way. Much of the supporting evidence is theoretical and mathematical, built on analogies and symmetries that may not hold perfectly in our universe. Our own space-time appears to be flat or slightly positively curved, not the anti-de Sitter shape required for the cleanest holographic calculations. Nonetheless, many physicists believe that the holographic approach is one of the most promising roads toward a complete theory of quantum gravity. It offers a way to bridge Einstein's geometric description of gravity with the probabilistic world of quantum mechanics. And it gives us a radically new way to think about the deepest questions of all. What is the universe? Where did it come from? And what is it made of? In summary, the holographic principle suggests space and time are emergent, not fundamental. All of reality may be a projection from a lower dimensional surface. Gravity, black holes, and the structure of a universe may be governed by laws of information. The universe could be fundamentally a quantum computer, encoding and unfolding informational patterns that create the illusion of space, matter, and time. This is not merely speculative philosophy. It is backed by serious mathematics, deeply rooted in quantum field theory, string theory, and general relativity. It has practical applications in areas like condensed matter physics and high-energy collisions, and it may eventually lead us to a unified theory of everything. Whether or not the universe truly functions like a hologram, the holographic principle forces us to confront the limits of human perception, the illusion of solidity, and the idea that the most real thing in the universe may not be atoms but information. Now we transition into loop quantum cosmology, LQC, a theory that emerges from loop quantum gravity, LQG, and aims to apply its principles specifically to the early universe. This framework doesn't just attempt to describe what created the universe. It completely reimagines the fundamental nature of space, time, and the very concept of the Big Bang itself. To understand loop quantum cosmology, we must first grasp the idea behind loop quantum gravity, the broader theory it stems from. LQG is one of the leading contenders in the quest for a quantum theory of gravity, a framework that unifies general relativity, which governs the very large, with quantum mechanics, which governs the very small. Unlike string theory, which posits extra dimensions and vibrating strings, LQG is built upon a more conservative approach. It does not assume a background spacetime. Instead, it tries to quantize spacetime itself. In LQG, space is not continuous but discrete, composed of finite chunks or quanta of space. These chunks are represented mathematically by networks called spin networks, which evolve over time into structures known as spin foams. Instead of imagining space as a smooth fabric, loop quantum gravity tells us that space is more like a finely woven mesh, and the threads of this mesh are fundamental units of area and volume, Planck-scale elements that cannot be subdivided further. Now, loop quantum cosmology takes these concepts and applies them to the entire universe. Specifically, it modifies the equations of cosmology, most notably the Friedmann equations, which describe the expansion of the universe under general relativity, to account for the quantum geometry of space at extremely small scales. One of the most revolutionary consequences of LQC is its resolution of the Big Bang singularity. In classical general relativity, the universe begins as a singularity, a point of infinite density, temperature, and curvature where the laws of physics break down. But this notion of a singularity has always been problematic. It signals the limits of our theories, a place where prediction becomes impossible. Loop quantum cosmology replaces the Big Bang singularity with a big bounce. According to this model, as the universe contracts toward extremely high densities, quantum gravitational effects become dominant and act like a repulsive force, preventing the formation of a singularity. Instead of an origin from nothing, the universe transitions from a previous contracting phase into our current expanding phase. In other words, what we perceive as the Big Bang was not the beginning of space and time, but a bounce from a prior cosmic epoch. Before our universe expanded, it may have undergone a period of contraction, governed by the same physical laws, but affected differently by quantum corrections to gravity. This turns the traditional narrative on its head. The universe didn't emerge from absolute nothingness, but from a pre-existing state shaped by quantum geometry. LQC predicts that when the universe reaches a critical density, near the Planck density, quantum effects become so strong that they halt and reverse gravitational collapse. This avoids infinite values for density and curvature, providing a non-singular beginning to spacetime. Mathematically, this is expressed by replacing the classical differential equations of general relativity with difference equations that reflect the discrete nature of spacetime in LQC. These quantum-corrected equations have been shown in multiple simulations to yield a bouncing universe under various initial conditions. But LQC goes even further. It offers specific, testable predictions about the early universe and cosmic inflation. For instance, it modifies the behavior of inflationary fields in such a way that it could potentially leave observable imprints in the cosmic microwave background, CMB. These imprints could include subtle variations in the power spectrum or new patterns in the polarization of the CMB, patterns that future telescopes might detect. Additionally, loop quantum cosmology suggests that the universe has a minimum volume. This is a direct consequence of the discretized nature of space. Just as matter is made of atoms and can't be divided infinitely, space itself is quantized and has a smallest possible unit. This minimum volume acts as a natural regulator, ensuring that the universe never truly reaches zero size. From a philosophical perspective, this has deep implications. It means the universe has no true beginning in the traditional sense. Instead of creation ex nihilo, something from nothing, we get a cyclical or pre-bounce view of reality, where space-time is eternal in some form, undergoing transitions that resemble cosmic rebirths. This leads naturally to questions about what came before the bounce. Was a universe just like ours? Was it fundamentally different? Could the laws of physics themselves evolve through such bounces in a kind of cosmic Darwinism? While LQC doesn't yet answer these questions definitively, it opens the door to a much larger cosmic history than standard cosmology allows. One of the strengths of LQC is that it's mathematically rigorous, yet conceptually intuitive. It maintains the general relativity insight that gravity is geometry, but reinterprets that geometry as fundamentally quantized. This makes it a natural playground for physicists seeking to merge quantum theory and gravity without the added complexities of string theories, extra dimensions, or brane worlds. However, LQC is not without its challenges. The field is still in development, and though it has yielded impressive results in symmetric models, like homogeneous and isotropic universes, extending it to full, inhomogeneous quantum spacetimes remains a major hurdle. There's also the question of observational confirmation. While it makes predictions that might show up in the CMB or large-scale structure surveys, none have yet been definitively observed. Despite these hurdles, the implications of loop quantum cosmology are immense. It provides a realistic and mathematically grounded alternative to the traditional Big Bang narrative. It avoids singularities, preserves the continuity of space and time, and offers a vision of the universe where quantum geometry dictates cosmic destiny. To summarize the key features of loop quantum cosmology, space is discrete, made of tiny Planck scale units. The Big Bang is replaced by a big bounce. The universe may have contracted before expanding. There is a minimum volume, avoiding singularities. Quantum corrections alter early universe dynamics, potentially affecting inflation and CMB signatures. The theory is rooted in a fully background-independent quantum theory of gravity. With this elegant picture, LQC allows us to peer beyond the Big Bang and imagine a universe that did not begin in a singular flash, but emerged cyclically or transitionally from a previous cosmic epoch, governed by the same deep principles of quantized space and gravity. Now we move into the no-boundary proposal, one of the most fascinating and conceptually daring ideas in the search for the origin of the universe. Developed by physicist Stephen Hawking and his collaborator James Hartle, this proposal redefines our understanding of space and time, not by focusing on what came before the Big Bang, but by questioning whether such a before is even meaningful in the first place. At its heart, the no-boundary proposal suggests that the universe didn't emerge from a specific point in space and time, but rather from a timeless, boundaryless quantum state. To grasp the radical nature of this theory, we need to temporarily let go of how we normally experience time. In classical cosmology, time is a one-way street. We imagine the Big Bang as a sharp beginning, the point where time itself started ticking, and from which everything, space, matter, energy laws, unfolded. But this view leads to a troubling problem, the singularity. In the traditional Big Bang model, the equations of general relativity break down at the moment of the singularity, resulting in infinite curvature, density, and temperature. It's the ultimate dead end of physics. Hawking and Hartle's no-boundary proposal resolves this issue by eliminating the singularity entirely, but it does so by dramatically reshaping the geometry of space-time. They propose that at the origin of the universe, time as we know it transitions into space. This is not metaphorical. It's a mathematical concept derived from quantum cosmology. In more technical terms, the no-boundary proposal is built upon Euclidean quantum gravity, where instead of treating time as a real parameter, it's rotated into what's called imaginary time, a mathematical technique similar to what is used in statistical mechanics and quantum field theory. In imaginary time, time behaves more like space, and this shift allows the geometry of the universe to be smooth and finite, like the surface of a sphere. Imagine a globe. It doesn't have a beginning or an edge in the north-south direction. It just curves smoothly. There's no boundary where the globe starts. It simply exists as a whole. Now apply this idea to four-dimensional space-time, where 3 dimensions of space and 1 of time behave analogously. In this model, the universe is finite but unbounded. It has no edges, no singularities, and crucially, no moment of creation in the conventional sense. This smooth, boundaryless geometry is described by a wave function of the universe, known as the Hartle-Hawking wave function. Instead of defining an initial state at a single moment in time, it defines a probability amplitude for the universe's entire history. The wave function gives the likelihood of different possible configurations of the universe emerging from this timeless, spaceless quantum realm. The no-boundary proposal implies that the laws of quantum mechanics apply even to the entire universe, and that the universe's beginning can be understood in the same way that we understand the behavior of subatomic particles, probabilistically, without the need for a sharp boundary condition or a singular point. Importantly, this proposal does not deny the universe had a beginning. It redefines what a beginning means. In this view, the beginning is not a point but a smooth cap on space-time, much like the rounded south pole of the Earth, where latitude lines converge but there is no edge or boundary. So, what caused this transition from imaginary time to real time, from this smooth, timeless origin to the universe we observe today? According to the no-boundary proposal, it happened through quantum tunneling. Just as particles in quantum mechanics can appear on the other side of energy barriers they classically shouldn't be able to cross, the universe tunneled from a timeless quantum state into a classical expanding universe governed by familiar spacetime. This tunneling is not something that happened in time, because time itself did not exist until the process occurred. Rather, it's a transition from a quantum realm without time to a classical realm with time. Much like water freezing into ice, where before there was only probability and geometry, and afterward there was a space-time continuum with evolving events. A particularly elegant feature of this theory is that it naturally leads to inflation. In many versions of the Holographic wave function, the most probable histories of the universe involve a rapid early expansion, similar to what the inflationary theory independently predicted. This gives the no-boundary proposal predictive power. It doesn't just describe an origin, but helps explain early universe dynamics. From a philosophical perspective, this proposal carries deep implications. It suggests that questions like, what came before the Big Bang, are meaningless, not because they're forbidden, but because time itself does not extend beyond the origin. The universe simply is. It emerges from a timeless, law-governed quantum state, like a wave function spreading out into the fabric of reality. However, the no-boundary proposal remains a subject of ongoing debate. While it has inspired significant interest, it's mathematically complex and challenging to test. Its reliance on imaginary time and Euclidean geometry makes it difficult to connect directly with observational data. That said, researchers have investigated whether this model might lead to distinctive signatures in the cosmic microwave background, CMB, or in the distribution of large-scale structure, offering potential, though not yet conclusive, ways to verify or falsify it. One of the strengths of this theory is its coherence with quantum mechanics. It treats the entire universe as a quantum system, removing the need for arbitrary initial conditions. And by eliminating the singularity, it avoids the mathematical and philosophical inconsistencies that plague classical cosmological models. To summarize the key insights of the no-boundary proposal, the universe has no boundary in space-time, no singular edge or starting point. Time transforms into space at the origin via imaginary time. The universe emerges from a quantum state without time or classical geometry. The Holographic wave function describes the universe's entire history probabilistically. This framework naturally predicts inflation, making it consistent with key observations. It challenges the very notion of a before or a traditional moment of creation. In essence, the no-boundary proposal offers a radical yet elegant reframing of the universe's origin, grounded in quantum principles and geometry. Rather than a flash from absolute nothingness, it envisions a smooth, probabilistic emergence from a timeless, boundaryless quantum state. A universe without edges, limits, or paradoxes defined not by what it came from, but by the shape of the laws that govern it. Moving forward, let's explore the Anthropic principle, a concept that shifts our focus from the physical origins of the universe to the conditions necessary for observers, like us, to exist within it. Unlike theories that seek to explain how the universe began, the Anthropic principle asks a different, often philosophical, question: why does the universe have the properties that allow life and consciousness to arise at all? The Anthropic principle emerges from a simple observation. The fundamental constants and laws of physics appear to be finely tuned to permit the existence of complex structures, including galaxies, stars, planets, and ultimately life. Slight variations in these constants, such as the strength of gravity, the charge of the electron, or the cosmological constant, could render the universe lifeless and barren. For instance, if gravity were slightly stronger or weaker, stars might never form or would burn out too quickly to support the development of life. At its core, the Anthropic principle recognizes this fine-tuning and attempts to explain it. It comes in different forms, each with its own implications and philosophical weight. The weak Anthropic principle, WAP, simply states that the universe's observed values of physical constants are restricted by the requirement that life exists to observe them. In other words, we shouldn't be surprised to find the universe compatible with our existence, because if it weren't, we wouldn't be here to notice. This is sometimes seen as a tautology, but it sets the groundwork for more profound interpretations. The strong anthropic principle, SAP, goes further, suggesting that the universe must have properties that inevitably give rise to conscious life at some stage. This implies a kind of necessity or purpose embedded in the cosmos, raising philosophical and even theological questions about the nature of existence. One of the reasons the anthropic principle gained significant attention is its relationship with modern cosmological models like the multiverse theory, which we'll discuss soon. If countless universes exist, each with different physical constants and laws, then it's no surprise that we find ourselves in one that supports life, because only such universes could harbor observers. The anthropic principle has also been invoked in attempts to explain the seemingly inexplicable smallness of the cosmological constant. The cosmological constant governs the accelerated expansion of the universe. Observations show it to be extremely small, yet positive. If it were significantly larger, galaxies would never form. The anthropic principle suggests that among many universes with varying cosmological constants, we exist in one finely tuned to allow galaxy formation, and thus life. Despite its intuitive appeal, the anthropic principle is not without controversy. Critics argue that it skirts the core question of why the universe has these properties, providing instead a kind of observational selection effect. Some see it as a philosophical cop-out rather than a scientific explanation, while others embrace it as a vital piece of the puzzle in a multiverse context. One way to make the anthropic principle scientifically fruitful is to connect it with testable theories like the string theory landscape or eternal inflation, which suggest an enormous number of possible vacuum states, each corresponding to a different universe with its own laws. Within this landscape, the anthropic principle can help explain why we observe our particular set of constants. From a broader perspective, the anthropic principle invites us to reconsider the relationship between observers and the cosmos. It highlights that the act of observation is not a passive process, but may be deeply intertwined with the very nature of reality. It also raises profound philosophical questions about the uniqueness of our universe and whether life is a rare fluke or an inevitable outcome of cosmic evolution. To summarize, the anthropic principle highlights the fine-tuning of physical constants necessary for life, explains this fine-tuning as a selection effect tied to the existence of observers, comes in weak and strong forms, differing in their philosophical implications, connects deeply with multiverse ideas, providing a context where many universes exist with varying properties, sparks debate about the limits of scientific explanation versus philosophical interpretation. While it may not provide a direct causal explanation for the universe's origin, the anthropic principle shapes how we understand our place in the cosmos and the conditions that make existence possible. It bridges cosmology with philosophy, raising questions that challenge both science and human curiosity. String gas cosmology is a fascinating and somewhat less mainstream approach to understanding the origins and structure of the universe that stems from ideas in string theory, one of the most ambitious frameworks in theoretical physics, attempting to unify all fundamental forces and particles into a single coherent description. Unlike the traditional Big Bang narrative, which describes the universe beginning as an incredibly hot, dense point that expands and cools, string gas cosmology proposes that the early universe was dominated by a gas of strings, one-dimensional fundamental objects whose vibrations give rise to the particles and forces we observe. These strings were not merely confined to a three-dimensional space, but lived in a higher-dimensional space-time, potentially consisting of 10 or 11 dimensions as suggested by superstring theory or M-theory. The core idea behind string gas cosmology is that in the very early universe, all spatial dimensions were compact and small, curled up in complex shapes often described mathematically by Calabi-Yau manifolds. In this primordial phase, the universe was filled with a hot, dense gas of strings winding around these compact dimensions. Some of these strings were closed loops, others were open strings with endpoints attached to higher dimensional membranes known as branes. What is particularly intriguing is that the interactions between these strings and branes dictated the dynamics of the universe's expansion and the unfolding of spatial dimensions. According to the theory, only 3 spatial dimensions manage to grow large and expand, becoming the vast universe we inhabit, while the others remain compactified and hidden at scales too small to detect. This dimensional selection mechanism is a remarkable feature of string gas cosmology because it offers a potential explanation for why our observable universe appears to have precisely 3 large spatial dimensions, a long-standing puzzle in cosmology and fundamental physics. The winding modes of strings, which wrap around compact dimensions, can prevent those dimensions from expanding. When these winding modes annihilate each other in certain dimensions, those dimensions are free to expand. The mathematics suggest that this process naturally favors 3 dimensions expanding while the others stay small, which aligns with our observations. Moreover, string gas cosmology has implications for the very early thermal history of the universe. The string gas can generate a nearly scale-invariant spectrum of density fluctuations, tiny variations in density that eventually grew into galaxies and large-scale cosmic structures. These fluctuations arise from the thermal and quantum behavior of strings in the primordial gas. This makes string gas cosmology a compelling alternative to the more traditional inflationary paradigm. Although the two are not mutually exclusive, researchers have explored how the thermal fluctuations of strings can leave imprints on the cosmic microwave background radiation, potentially observable by current or future precision cosmological experiments. Another interesting aspect of string gas cosmology is how it handles the singularity problem. Traditional Big Bang theory predicts an initial singularity where densities and curvatures become infinite, marking a breakdown of physical laws. However, because string theory inherently includes a minimum length scale, the string length, it naturally introduces a cutoff that avoids these infinities. The string gas phase can be thought of as a pre-Big Bang epoch, where the classical singularity is replaced by a more fundamental, non-singular stringy state. This resonates with other quantum gravity-inspired cosmologies that seek to tame or eliminate the Big Bang singularity. String gas cosmology also introduces the possibility of novel phenomena, such as cosmic superstrings, extended, macroscopic string-like objects that might form during the early universe's evolution. These cosmic superstrings would differ from fundamental strings by their immense length and potentially observable gravitational effects, such as generating gravitational waves or lensing distant light sources. Detecting such cosmic superstrings would provide direct evidence for string theory and offer a window into the universe's earliest moments. Despite its elegance and potential, string gas cosmology faces significant theoretical challenges. Calculations in string theory are notoriously difficult, especially in regimes involving strong coupling and time-dependent backgrounds like an expanding universe. Also, the mechanisms by which strings and branes interact to select 3 large spatial dimensions require further rigorous mathematical underpinning and phenomenological validation. Critics argue that without direct observational evidence, string gas cosmology remains speculative, although its predictions about cosmic fluctuations and cosmic superstrings keep it actively researched. In addition, the connection between string gas cosmology and other string theory-based cosmological models, such as the Ekpyrotic and Cyclic universe models, is an area of ongoing investigation. These models share common roots in higher dimensional physics and brane dynamics, but differ in their descriptions of the universe's origin and evolution. String gas cosmology tends to emphasize a hot, dense, thermal phase dominated by stringy matter, whereas Ekpyrotic and Cyclic models focus on collisions between branes or cycles of contraction and expansion. On a philosophical level, string gas cosmology invites us to think about the universe not just as a collection of particles and forces in spacetime, but as a vibrant, dynamic system of fundamental strings whose interactions determine the very fabric and dimensionality of reality. It elevates the role of geometry and topology, suggesting that the universe's large-scale structure is a direct consequence of microscopic stringy processes in a high-dimensional arena. This perspective challenges and enriches our understanding of the cosmos, blending quantum mechanics, thermodynamics, and geometry into a unified narrative. As the field progresses, researchers are developing increasingly sophisticated mathematical tools and computational simulations to explore string gas cosmology's predictions and compare them with astrophysical data. Observations of the cosmic microwave background, gravitational waves, and large-scale structure provide testing grounds for the theory's viability. While direct detection of strings or superstrings remains elusive, indirect evidence through cosmological signatures continues to motivate efforts to refine the model. In summary, string gas cosmology offers a bold alternative framework to understand the universe's birth and structure by incorporating the fundamental principles of string theory. It proposes a primordial phase dominated by a hot gas of fundamental strings in a compact higher-dimensional space, with interactions that naturally explain why three spatial dimensions expanded. It addresses key cosmological problems like the singularity and the origin of fluctuations, introduces novel observable phenomena, and provides fertile ground for connecting fundamental physics with cosmology. Having explored string gas cosmology in considerable depth, the next step in our journey through the landscape of cosmological theories leads us to the causal set theory, an approach that reimagines spacetime itself in a discrete, fundamental way, quite unlike the smooth continuum envisioned by general relativity. Causal set theory represents one of the most intriguing and unconventional attempts to understand the fundamental structure of spacetime and the origins of a universe. Unlike traditional cosmological models that rely on the smooth geometry of general relativity, causal set theory posits that spacetime is fundamentally discrete, composed of individual, irreducible elements linked by causal relationships. Think of it as replacing the continuous fabric of the cosmos with a deep, granular scaffold of spacetime, atoms, connected by a network of cause and effect. Each of these elements is not embedded in space and time. They are space and time. This radical shift changes how we think about the nature of the universe, especially when considering the extreme conditions near the supposed beginning of everything. At its core, causal set theory suggests that the fabric of spacetime is a partially ordered set, or posit, where the elements are discrete events and the order between them represents causality, the idea that one event can influence another. This causal structure forms the skeleton upon which the geometry of spacetime is built. According to the theory, if one knows the causal relationships between events and the number of such events, then the geometry of the underlying spacetime, including dimensions, volume, and curvature, can in principle be reconstructed. This is a profound statement because it implies that causality and counting are all that is needed to recreate the geometry of the universe, offering a powerful simplification of physical law at the most fundamental level. One of the key motivations for causal set theory is the problem of combining general relativity with quantum mechanics. General relativity treats spacetime as a smooth, continuous manifold, while quantum mechanics, particularly quantum field theory, introduces intrinsic discreteness and probabilistic behavior. These conceptual differences create profound mathematical and physical incompatibilities. By postulating that spacetime is discrete, causal set theory circumvents the infinities that plague many quantum gravity approaches. In a causal set, there's no room for arbitrarily small regions of space or infinitely short durations of time, a built-in safeguard against the divergences that challenge modern physics. Another appeal of causal set theory lies in its minimalistic assumptions. Instead of invoking complex extra dimensions, exotic matter, or mathematical abstractions like strings or loops, it begins with a very basic foundation: discrete events and their causal relations. This simplicity makes the theory conceptually elegant and, some argue, closer in spirit to Occam's razor than more elaborate theories like string theory. Moreover, it aligns with the causal structure already embedded in relativity, preserving one of Einstein's central insights while taking it further by making causality the cornerstone of existence itself. Within this framework, the universe's expansion and the emergence of large-scale structures are thought to result from the sequential birth of new space-time elements. Each new element is randomly sprinkled into the set in a way that respects the causal structure. That is, no element can causally influence a past event. This sequential growth process gives rise to a dynamic causal set, and the statistical properties of this growth model can reproduce features of familiar spacetime geometries when viewed at large scales. Thus, our universe, with its vast stretches of space and time, may emerge from the accumulation of countless microscopic causal events governed by a few simple rules. Causal set theory also proposes an intriguing interpretation of cosmological entropy and the arrow of time. Since the causal set grows in a preferred direction, new elements are added only to the future. It naturally incorporates time asymmetry. This directionality mirrors the irreversible flow of time we experience and is consistent with the second law of thermodynamics, which states that entropy tends to increase over time. Thus, the growth of the causal set itself may underlie the arrow of time, offering a deep explanation for one of the most fundamental features of our reality. When applied to the early universe, causal set theory suggests that the origin of spacetime wasn't a singular explosive event, like the Big Bang in its traditional form, but rather the emergence of the first elements in the causal network. In this view, the universe began as a single causate element, and the passage of time is simply the accumulation of more elements, each linked causally to others. There's no need for a pre-existing space or time. Space and time emerge as more elements join the network. This eliminates the need for an initial singularity and provides a graceful origin scenario that sidesteps the mathematical breakdowns encountered in classical general relativity. Moreover, this framework may have testable implications. For instance, if space-time is made of discrete units, then over incredibly vast distances, the travel of light or other particles might show subtle statistical irregularities, tiny fluctuations in arrival times or directions that deviate from what a continuous spacetime would predict. Although such effects would be extraordinarily small and difficult to measure, they lie within the realm of possibility for future astrophysical observations or high-precision experiments. One particularly interesting prediction of causal set theory is the suppression of the cosmological constant problem. In standard cosmology, quantum field theory predicts a vacuum energy density, the cosmological constant, that is vastly larger than what we observe. This discrepancy is one of the great unsolved mysteries in physics. However, in causal set theory, the vacuum energy naturally fluctuates due to the discrete nature of spacetime. These fluctuations can, in principle, average out to a small value that matches observations, thus offering a potential solution to this troubling puzzle. Despite its elegance and simplicity, causal set theory is not without its challenges. One major difficulty lies in embedding a causal set into a known spacetime manifold in a way that preserves all its geometric properties. This is a non-trivial mathematical problem and requires sophisticated algorithms and statistical techniques. Furthermore, the theory currently lacks a fully developed dynamical law comparable to Einstein's field equations. While the sequential growth model offers a glimpse into how the universe might evolve, a comprehensive dynamical framework that predicts all aspects of space-time curvature and matter interactions is still under development. Nevertheless, work continues on bridging the theory with other areas of physics. There are attempts to couple causal sets with matter fields, to develop quantum theories on causal sets, and to understand black hole thermodynamics from a causal set perspective. These efforts aim to show that causal set theory can reproduce not just the general shape of spacetime, but also its rich dynamical behavior and the complexity of interactions that make up the observable universe. Ultimately, causal set theory invites us to rethink the very meaning of existence. If spacetime is not a continuous stage upon which events play out, but rather the outcome of fundamental events and their causal connections, then our universe is not just made of matter and energy, but of the structure of logic and causality itself. This shift echoes deeper philosophical questions about the nature of time, existence, and the fundamental rules that govern reality. Questions that have occupied humanity for millennia and now find expression in the cutting edge of theoretical physics. Having now explored causal set theory in full depth, we are ready to move on to the next cosmological approach, the emergent gravity theory, a provocative framework that proposes gravity and spacetime themselves are not fundamental forces but arise from deeper, more fundamental quantum informational processes. Emergent gravity theory offers a radically different way to look at gravity and the structure of the universe. At its heart lies a powerful idea that gravity is not a fundamental force like electromagnetism or the strong and weak nuclear forces, but rather an emergent phenomenon, something that arises from deeper, more fundamental constituents of reality, possibly related to information theory and quantum mechanics. In this perspective, spacetime and gravity are not building blocks of nature. They are consequences of the statistical behavior of underlying microscopic degrees of freedom. This concept is often compared to how the temperature of a gas isn't a fundamental property of atoms, but something that arises when you consider the collective motion of a large number of them. The origins of emergent gravity can be traced back to the ideas of physicists like Jacob Bekenstein and Stephen Hawking, who first connected thermodynamics and gravity by showing that black holes possess entropy and radiate energy. These discoveries hinted at a deep connection between the geometry of spacetime and thermodynamic laws. In the 1990s and early 2000s, physicist Ted Jacobson made a bold leap by showing that Einstein's equations, the foundation of general relativity, could be derived from thermodynamic principles. In other words, he demonstrated that gravity could be understood as an equation of state, similar to the way pressure and temperature relate to each other in a gas. This insight laid the groundwork for the emergent gravity hypothesis. Later, physicists like Eric Verland extended this idea, arguing that gravity is not a fundamental interaction but emerges from changes in the information associated with the positions of material bodies. In Verland's framework, the presence of mass or energy affects the information content of spacetime, creating what we perceive as gravitational attraction. This idea aligns with the broader notion that space and time are manifestations of a deeper, information-theoretic structure. If information changes, if the underlying quantum bits of reality are rearranged, then the geometry of space itself shifts, and gravity emerges as a result. One of the most compelling motivations for emergent gravity theory is the attempt to resolve long-standing problems in physics, such as the nature of dark matter and dark energy. Traditional models of the universe require that most of the cosmos be composed of these invisible, unknown substances to account for galaxy rotation curves and the accelerated expansion of the universe. Verland's version of emergent gravity proposes an alternative explanation, that these cosmic phenomena are not the result of unseen matter, but rather emerge from the underlying information structure of spacetime in a way that mimics the gravitational effects attributed to dark matter. While this idea is still being tested and debated, it opens up the possibility that what we call dark matter could be a sign that our current understanding of gravity is incomplete. Another intriguing implication of emergent gravity is its relationship with holography. The holographic principle, which we'll explore in its own section later, proposes that all the information contained in a volume of space can be encoded on its boundary. Emergent gravity often incorporates this principle, suggesting that the three-dimensional reality we experience arises from two-dimensional information on a cosmic horizon. In this sense, gravity and spacetime are like the 3D image in a hologram, not fundamental objects, but emergent illusions from a deeper informational source. This shift in perspective changes the questions we ask about the universe. Instead of asking why gravity behaves the way it does, we begin asking what the underlying bits of information are and how they interact. It challenges the traditional view of spacetime as a passive stage and instead sees it as a dynamic, emergent entity shaped by quantum entanglement and informational entropy. This means that everything, from black holes to the shape of the universe, might be the byproduct of microscopic informational rules playing out at a vast cosmic scale. Furthermore, the emergent view provides a fresh framework for addressing the quantum gravity problem. Since gravity arises from quantum information, we no longer need to quantize gravity in the traditional sense. Instead, we can aim to understand the microscopic structure from which both quantum mechanics and gravity emerge. This could potentially unify physics under a single framework, dissolving the boundary between spacetime and quantum theory, and explaining gravity without needing gravitons or exotic string-based mechanisms. Emergent gravity also has implications for the early universe. If spacetime itself emerged from a dense, chaotic sea of quantum information, then the initial state of the universe was not a singularity in the classical sense, but a transition from pre-geometric, information-rich quantum chaos into the orderly spacetime we observe today. This might offer a resolution to the singularity problem and suggest that the universe's birth was less like an explosion and more like a phase transition, akin to water freezing into ice, where a new structure crystallizes from disordered components. This line of reasoning could also shed light on the arrow of time. If time emerges from the increase of informational entropy, then the direction of time, from past to future, is simply a byproduct of the universe evolving from low to high information complexity. As the universe unpacks more information over time, space-time expands, structures form, and gravity appears to guide matter through this evolving tapestry. Although emergent gravity remains a developing field with many open questions, it provides a fertile ground for exploration. It encourages us to think of the universe not as a machine with fixed parts, but as a dynamic, evolving computation. The cosmos becomes a quantum information processor, and space-time is its interface, something that emerges, evolves, and potentially even disappears under extreme conditions like black holes or the early universe. Despite its promise, emergent gravity also faces challenges. It must not only reproduce the predictions of general relativity, but also explain phenomena in regions where relativity breaks down, such as inside black holes or during the early moments after the Big Bang. Moreover, it must make testable predictions that distinguish it from other models, a difficult task given that many of its effects only emerge at very large or very small scales. Nonetheless, its conceptual elegance and its potential to unify disparate areas of physics continue to attract attention. In summary, emergent gravity theory reimagines gravity not as a fundamental force, but as a statistical phenomenon that arises from the quantum informational structure of the universe. It draws deep connections between thermodynamics, quantum mechanics, and space-time geometry, offering a bold vision of a cosmos where reality itself, including the very space we move through, is a consequence of invisible informational dynamics playing out beneath the surface of what we observe. Having now completed a full exploration of emergent gravity theory, we are ready to transition into the next major cosmological model, the vacuum decay or false vacuum theory, an unsettling idea that the very fabric of our universe might be in a temporary state, with the potential to suddenly collapse into a more stable configuration, altering all the laws of nature in the process. The vacuum decay or false vacuum theory introduces one of the most chilling possibilities in theoretical physics. The idea that the universe as we know it is not in its most stable state, but instead exists in what's called a false vacuum. To understand this, we must begin with the concept of a vacuum in quantum field theory. Unlike the everyday notion of a vacuum as simply empty space, in physics, a vacuum refers to the lowest possible energy state of a quantum field. However, what seems to be the lowest energy state may not actually be the true minimum. A false vacuum is a metastable state. It appears stable and can persist for billions of years, but in reality, it harbors the potential to decay into a lower, more stable state called the true vacuum. In this theory, the vacuum of space contains a certain energy density, often referred to as vacuum energy, and this energy determines the structure of the universe and the behavior of the fundamental forces. If our universe resides in a false vacuum, that means a more stable vacuum state exists with a different and lower energy level. Transitioning from a false to a true vacuum wouldn't be a gradual process. Instead, it would be catastrophic. A quantum tunneling event could occur anywhere in space, creating a bubble of true vacuum that expands at the speed of light. As this bubble sweeps through the universe, it would redefine the laws of physics inside it, potentially destroying all matter and structure as we know it. This sounds like pure science fiction, but it's grounded in real, testable physics. The theory emerges naturally from quantum field theory, particularly in models involving scalar fields like the Higgs field. When the Higgs boson was discovered at the Large Hadron Collider in 2012, measurements of its mass and that of the top quark revealed something unexpected. These values suggest that the shape of the Higgs potential, the energy landscape in which the Higgs field operates, might not place us in the most stable configuration. Instead, we might be perched on a gentle slope that leads down into a deeper, true vacuum state. This revelation caused a stir among physicists, as it suggested that our universe is perched in a precarious energy state that might not be permanent. The possibility of vacuum decay raises profound questions. Why does the universe appear stable if it's not in the true vacuum? How likely is it that such a decay event could happen? And if it does occur, what happens next? One answer lies in the immense timescales involved. Even if the universe is in a false vacuum, the probability of a transition occurring might be extraordinarily low, so low that it would take many trillions of years before it happens. In this sense, the threat is real but remote. Nonetheless, it's not something we can predict or prevent, since such an event would arrive without warning and propagate faster than the speed of light, obliterating everything in its path instantaneously. There is a poetic cruelty in this scenario. Imagine a universe so delicately balanced that a single fluctuation, one allowed by the uncertainty principle of quantum mechanics, could spell its undoing. Unlike other cosmic apocalypses, such as the Big Crunch or heat death, which play out over unimaginably long timescales, vacuum decay is sudden, silent, and final. It speaks to the fragility of reality itself, and how the fabric of existence is a precarious balance of energies. We often think of the laws of physics as eternal and unchangeable, but vacuum decay theory reminds us that these laws depend on the vacuum state. And if that changes, everything changes. This theory is not merely a theoretical curiosity. It also plays a role in discussions about the ultimate fate of the universe. If the universe is indeed in a false vacuum, then vacuum decay might be the true endgame. It also intertwines with other cosmological theories, especially those involving inflation and scalar fields. In fact, some versions of eternal inflation suggest that pocket universes could form in different vacuum states, and transitions between these states might generate completely distinct physical realities with different constants and particles. In that sense, vacuum decay is a mechanism not only for destruction, but also for the birth of entirely new universes. Interestingly, some physicists propose that vacuum decay could have already happened in some distant part of the universe, and we just haven't seen the resulting bubble yet, because it's traveling toward us at the speed of light. It's possible, however unlikely, that the very space around us is already doomed, and we simply haven't noticed. This idea, while terrifying, is balanced by the recognition that such decay events are deeply improbable given the observed age and stability of our universe. After all, we've made it this far, 13.8 billion years without incident, which suggests that either we're not in a false vacuum, or that vacuum decay is such a rare event that it has yet to happen in our observable patch of the cosmos. On a more speculative note, some theories even suggest that advanced civilizations could trigger or avoid vacuum decay. In hypothetical scenarios involving quantum manipulation or exotic particles, it's theorized that future civilizations might either precipitate such a collapse accidentally or attempt to forestall it by stabilizing the false vacuum. However, These ideas remain speculative and rest on technologies far beyond our current capabilities. Philosophically, vacuum decay theory forces us to confront a deeply unsettling truth. The universe doesn't owe us stability. The rules that govern everything, from the dance of electrons and atoms to the arc of galaxies across the sky, could be swept away in a moment, replaced by laws we can't imagine and conditions in which life, matter, or even space and time may not exist. The false vacuum, if real, hangs over us like a silent executioner, invisible, indifferent, and inescapable. This theory also reshapes the discussion around the Anthropic principle. If countless regions of the multiverse exist, each with its own vacuum state, then we live in a false vacuum simply because it's one of the few that allows for the existence of observers. In that case, our survival thus far is not evidence of the universe's stability, but a selection effect. We exist in a vacuum state that hasn't decayed yet because only such regions are compatible with life. This perspective adds an eerie layer of determinism to the universe, as though we are mere passengers in a cosmic ship floating atop a sea of potentially fatal quantum transitions. Having now covered the vacuum decay or false vacuum theory in detail, we're prepared to move forward into one of the most provocative and abstract proposals in all of theoretical physics, Tegmark's mathematical universe hypothesis. Now we arrive at one of the most abstract and deeply philosophical ideas about the origin of the universe, Tegmark's mathematical universe hypothesis. Proposed by physicist and cosmologist Max Tegmark, this hypothesis boldly asserts that the universe doesn't merely follow mathematical laws, it is mathematics. According to this idea, all physical reality is ultimately a mathematical structure, and every mathematical structure exists in its own right as a form of physical reality. This means that the fabric of our universe is not just described by math. It fundamentally is math. To appreciate the full scope of this theory, we must first recognize the profound success of mathematics in describing the universe. From Newton's laws of motion to Einstein's equations of general relativity and the intricate frameworks of quantum mechanics, mathematical equations have proven astonishingly accurate in predicting how the universe behaves. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner once described it, is not just a tool of convenience. It may be a clue to something deeper. Tegmark takes this observation to its ultimate conclusion. Perhaps the universe is not just governed by mathematical laws. Perhaps it is nothing but a mathematical object. In this view, the universe is a complex, self-consistent solution to a set of mathematical equations. Everything that exists, particles, forces, time, space, consciousness, arises from and is embedded within this mathematical structure. If this is true, then our cosmos is just one of infinitely many possible universes, each corresponding to a different mathematical structure. Every logically coherent mathematical system exists somewhere, not as a mere abstract concept, but as a physical reality in its own domain. This concept leads directly to what Tegmark calls the level 4 multiverse. In contrast to the level 1 multiverse, other regions of space beyond our cosmic horizon, level 2, bubbles of universes with different physical constants, and level 3, many worlds of quantum mechanics. Level 4 posits a far more radical landscape. All mathematically possible universes exist. These universes do not share our space, time, or physical laws. They're completely separate realms, each defined by a different set of equations. Our universe, then, is just one mathematical structure among an infinite set. Critically, Tegmark argues that if we accept that external physical reality exists independently of us, and if mathematics is the only language precise enough to describe it, then the conclusion that the universe is mathematics itself becomes unavoidable. In his view, subjective perceptions and physical substance are not fundamental. Instead, what's fundamentally real is the abstract, timeless structure of mathematics, and consciousness is simply the result of complex patterns arising within this structure. Of course, This raises deep questions about what it means for something to exist. In traditional thinking, existence implies being part of space-time, having matter or energy. But in Tegmark's hypothesis, existence is redefined. To exist is to be mathematically possible. Anything that can be described by a consistent set of mathematical rules, a four-dimensional space-time, a universe of entirely different dimensions and constants, or even a completely alien logic system, has physical existence in its own right. The boundary between mathematics and reality dissolves completely. One of the implications of the mathematical universe hypothesis is a new perspective on why the universe has the properties it does. If all mathematical structures exist, then there is no need to explain why our universe has these particular laws. It simply happens to be the one we observe because it supports observers like us. In this way, the hypothesis overlaps with the Anthropic principle, providing a framework in which our universe is one of the relatively rare mathematical structures that permits life and consciousness to arise. This hypothesis also challenges the traditional hierarchy of reality. Typically, we think of matter and energy as the base level, with abstract concepts like mathematics sitting atop them. Tegmark inverts this. Mathematics is the foundation, and matter, energy, and even space-time are emergent properties of that mathematical structure. This inversion is radical, but not without precedent. Quantum mechanics and general relativity already blur the lines between physical substance and mathematical abstraction, suggesting that reality is far stranger than common sense allows. Furthermore, the mathematical universe hypothesis opens up entirely new realms for cosmology and ontology. If true, then theoretical physicists are not merely describing the universe. They are discovering which mathematical structure we live in. The ultimate goal becomes identifying the precise mathematical system that defines our cosmos. And if such a structure is found and understood, it could offer the most complete and elegant explanation of the universe's existence, not as a result of a creator or an accident, but as a necessary consequence of mathematical existence itself. Of course, this theory is not without criticism. One major challenge is that it may not be falsifiable. If all mathematical structures exist, how can we test this? By definition, we can only observe the universe we're in, so the existence of other mathematical realities may forever lie beyond empirical science. Critics argue that while the idea is intellectually stimulating, it might remain in the realm of metaphysics rather than physics unless it yields specific, testable predictions about our universe. Nevertheless, Tegmark suggests that the hypothesis is indirectly testable. For example, if the universe is a mathematical structure, then its laws should exhibit maximal simplicity and elegance. Discovering such laws would lend support to the hypothesis. Moreover, if we find that consciousness and self-awareness can be simulated or emerge from mathematical patterns, as in artificial intelligence or neural networks, it could further support the view that mind and matter are manifestations of mathematical relations. Another intriguing angle is that this hypothesis redefines the search for extraterrestrial intelligence. If all mathematical structures exist, then there could be forms of life and intelligence far beyond our understanding, not just in other universes with different physics, but in entirely different logical frameworks. Some thinkers speculate that even certain mathematical patterns or algorithms might be considered alive or conscious in their own domain. This stretches the definition of life and reality, but within the context of Tegmark's hypothesis, it is entirely logical. The mathematical universe hypothesis also resonates with ancient philosophical traditions that viewed reality as fundamentally numerical or geometric. From the Pythagoreans, who believed all is number, to Plato's realm of ideal forms, the idea that abstract mathematics underlies the physical world has deep roots. Tegmark's proposal can be seen as a modern scientific articulation of these ancient intuitions, grounded not in mysticism, but in the rigorous framework of theoretical physics and mathematical logic. In conclusion, Tegmark's mathematical universe hypothesis offers a radical reimagining of reality. one in which the universe is not a collection of particles or forces, but a timeless, abstract, and self-consistent mathematical structure. Everything we observe, including ourselves, is a manifestation of that structure. While difficult to test directly, the hypothesis provides a compelling framework for understanding why the universe exists, why it behaves as it does, and why mathematics has such extraordinary power to describe the cosmos. It is a vision of reality that transcends traditional physicalism, suggesting that the ultimate answer to the question, what created the universe, might be nothing more and nothing less than pure mathematics. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.